In Project 3, we wrote a ray tracing algorithm assuming that light travels in a straight line. However, there are cases when light takes a curved path, and this is what we're doing in this project. The first method we use to model the air density, or to be more specific, the change of index of refraction, is equal slab method. In this case, we have slabs of equal height, and each of the slabs represent a different index of refraction. These are some of the Mirage images we rendered in interior lighting using 10, 100, and 700 slabs, respectively. The problem with the previous method is that it takes a very long time to render. So we introduced a modified version of the slab method. In this modified version, we're no longer fixing the height of the slab. Instead, we're fixing the time that each ray travels in the slab. And these are some of the images we rendered. This is a demonstration that we can set any block of the scene to be a certain index of refraction.
The last technique we used assumes that index of refraction stays constant at points with the same height. Obviously, that's not true in more complex scenes, so we wanted to relax that assumption. We go about it using general equations based on Fermat's principles. These differential equations are solved with Euler integration in order to get the final path that the light follows. We apply this more general ray tracing technique to gradient index optics lenses. These are lenses in which the index of refraction changes throughout the material. Such lenses theoretically have desirable qualities such as fewer aberrations that could cause visible artifacts in final images, and it's theorized that the human eye actually has various index of refraction. Here's the specifics for the Grin lens we use. Note that it was actually designed for use in fiber optics cables, but we used it for our ray tracing task. We modify the ray tracing algorithm by placing the Grin lens in front of the camera and tracing scenes through the lens, or tracing light rays through the lens into the scene using the Euler integration technique. Here are a few examples of such ray tracing from the origin point, that is the camera sensor, through the lens into the scene. Here's a rendering of CB Bunny, and here a rendering of CB Dragons at different quality levels and different focus points.